Damped harmonic motion occurs when we assume some sort of friction. For example, with the spring, there's air resistance that will slow down the spring. So here our spring is moving, and we see that it doesn't come back up as high or go down as low as it did at first. And the height is going to keep decreasing over time as our spring goes up and down. So this is damped harmonic motion. Damped harmonic motion can be modeled by y equals k e to the negative ct of sine of omega t, or y equals k e to the negative ct cosine of omega t, where c is greater than 0. K represents the initial amplitude, 2 pi over omega is the period, and c is the dampening constant. So let's try this problem. Find a function for the damped harmonic motion using y equals k e to the negative ct sine of omega t, where k equals 3, c equals 2, and the frequency is 5. So we know that k is 3, so we have y equals 3e, c is 2, negative 2t sine. Now we have to find omega, and we were given the frequency, which is omega over 2 pi. So we have that equals 5. So omega equals 10 pi. So we have sine of 10 pi t, and that's our function. And then it asks us to graph. And here's a graph of our harmonic motion. Now let's have you try. Find a function for a damped harmonic motion using y equals k e to the negative ct sine of omega t, where k equals 2, c equals 3, f equals 4, and then graph the function. So go ahead and pause the video, and when you're ready, come back and look at the answer. So k equals 2. So we have y equals 2e, c equals 3 to negative 3t, sine, our frequency is 4. So frequency is omega over 2 pi, so and that has to equal 4, so omega equals 8 pi. So sine of 8 pi t. And then it asks us to graph. And here is our damped harmonic motion.